All right, welcome back. Today we're going to go through 5.8, which is applications of logarithmic scales. This ends up being the last section in this chapter of exponents and logarithms. And it looks at a variety of types of applications that, that are logarithmic in nature. And you'll always be given a formula for how these work. Many of them work essentially kind of similarly, and they end up comparing some sort of, with earthquake intensity, comparing intensities of earthquakes, and relating that to a measurement, commonly known as Richter scale, but that's technically not quite true either. But relating an earthquake's intensity to its given measurement. We're also going to look at sound levels with decibels, and we're also going to look at some chemistry with pH and comparing acidity or alkalinity. So this one starts off with an example about earthquake intensity, and it says, okay, here's your formula as m is equal to log of I over I naught. M is what you commonly think of as the measurement of how strong an earthquake is. And so when you hear about in the news that this had an intensity of an 8.3 or 7.4, these things are logarithmic, which means essentially that every additional 1 point on this earthquake scale is a factor of 10 in intensity. And so if something seems like it's well, this was a 7.7 instead of a 7.2, it actually ends up being a huge significant difference in intensity, even though it's just maybe even less than 1 on your measurement scale for an earthquake. So that's kind of the nature of how these things work, and that's why we use a logarithmic scale, is because to compare things that differ by 10,000 in intensity or 100,000 in intensity, it becomes kind of meaningless if we use a linear scale. So we end up using a logarithmic scale just so that we can make sense of graphical information, and we can compare things easier. All right, so here's this formula. M is equal to log I over I naught. I naught is this kind of, this abstract idea, and it ends up essentially being your benchmark of the lowest possible measurement of some sort of seismic activity. So the lowest possible shaking that the earth can do ends up being I naught. I ends up being the intensity of the earthquake that you're studying. And if we take the logarithm of that ratio, that's how we convert it into this. We can think of M as like a score for an earthquake. Well, this one was a 7.2 or an 8.9 or whatever it ends up being. Okay, so if that's our formula, notice that these will all be in base 10. And so often our strategy is going to be to swap it around between exponent form and log form. All right, so number 1, earthquake in 1933 in Japan has a magnitude of 8.9. 1976 earthquake in Guatemala has a magnitude of 7.5. So the Japan one is larger. How many times more intense was this earthquake in Japan? So it's not looking for a ratio of 8.9 to 7.5. We're going to convert this to this idea of I. So let's start off by looking at what happened in Japan. And so in Japan, we have this formula, and we're going to take M of the Japanese earthquake is equal to logarithm of I of the Japanese earthquake over I naught. So as often will be the case, we're going to swap this around to an exponent form, and so it's going to end up looking like this. It's going to look like Ij, so the intensity of the Japanese earthquake, over I naught, which is this reference intensity, is equal to 10 to the mj. If I solve that for ij, it looks like this. Ij is equal to I naught times 10 to the. Now mj is our measurement of that Japanese earthquake, which is an 8.9. Okay, so before we go further, just to clarify, this ij represents the intensity of the Japanese earthquake, but it's this abstract measurement. So we're not really going to have a number in for that, but we are going to compare it to our next earthquake. And so we'll use that as a comparison. So let's switch gears to the Guatemala. And if we start with mg is equal to logarithm ig I naught. And if we do the same thing, ig will equal to, I just skip some of that step maybe, this ends up being ig is equal to I naught times 10 to the 7.5. All right, so what we're trying to do here is that we're trying to compare how many more times intense, how many times more intense the Japanese earthquake is to the Guatemala earthquake. Well, if you're trying to compare how many times larger this is than that is, you're taking a ratio of them, right? And so now what we need, therefore, is we need a ratio. The larger one is the Japanese, and the smaller one is the Guatemalan. And so ij over I naught will give us this comparison of intensity. Now notice what happens here, is this ends up being I naught times 10 to the 8.9 over I naught times 10 to the 7.5. These factors of I naught divide out. And this ends up being equal to 10 to the 8.9 divided by 10 to the 7.5. So what we're able to do, of course, is subtract those exponents because we're dividing. And this ends up being equal to 10 to the 1.4. So 10 to the 1.4. If we take that and push that into our calculator, then this ends up being equal to 25.1. Therefore, Japan earthquake was 5 times larger. But what you want to, how you commonly are going to be looking at this is what this comes down to is the fact that I1 divided by I2, if we're comparing the intensity of two of these earthquakes, and this will come down to 10 to the M1 minus M2. So what this will often come down to is if we're comparing two earthquake intensities, and if I say I1 divided by I2, if we're comparing the intensities of two earthquakes, it'll often come down to this, is that factor of how many times stronger this earthquake is than that earthquake will equal to the 10 to the difference in their measurements. And so this essentially is what this all boils down to. And this ends up being a useful form of comparing these two earthquakes, is the ratio of those the ratio of the intensities is equal to the difference of their Richter scale measurement, 10 to the exponent of that difference. All right, so we're going to do a similar thing with comparing sound loudness. Sound is measured in a unit called decibels. Our intensity of sound has this formula where dB is equal to 10 log I over I naught, where I is your sound intensity and I naught is your reference intensity. The only difference between this and our earthquake formula is this factor of 10. And really what that relates to is the fact that we are looking at decibels. And the fact that 10 decibels is equal to 1 bell. And if you think about what happens with our prefixes and metric measurements, decibels is commonly what we use, but technically, if we convert this all to bells first and just divide your number of decibels by 10, then that 10 divides out of this formula, and we end up just, well, it kind of ends up being simpler. But it is commonly, we do talk about decibels. When we're talking about sound, we don't really talk about bells, just because the numbers are more, make more sense to us to compare small changes in sound. And so we will use decibels in this question. Question number 2 says normal conversation has a decibel level of approximately 60 decibels, whereas a power saw, much louder, is 110 decibels. How many times more intense is the sound of a power saw compared to the sound of a normal conversation? Okay, so let's start off by breaking this into the 2 pieces. Our conversation ends up being equal to, so our formula is decibels for conversation is equal to 10 logarithm intensity of that conversation over I naught. And again, IC ends up kind of measuring this abstract idea of how intense this sound is. It has to do with the measurement of the sound waves. I naught ends up being this abstract idea of the lowest threshold of hearing. So don't worry too much about those, but we won't be asked to solve for those individually. We will be looking at the ratio of IC over IP, I guess, for power saw. And so to move ahead with this ends up being 60 is equal to 10 log IC over I naught. Dealing with 60 decibels. Now, as we've seen this before, we should divide both sides by 10 to get that logarithm by itself. And this step really is where we're converting from decibels to bells. And so it's 6 bells is equal to logarithm of IC over I naught. Now we swap around to exponent form. This is base 10. So this ratio of IC to I naught is equal to 10 to the 6. And if we solve this for IC, this ends up being IC is equal to I naught times 10 to the 6. If we do the same thing for a power saw, we end up with decibels of our power saw is equal to 10 logarithm the intensity of the power saw over I naught. And we end up with 110. 10 log IP over I naught. Dividing both sides by 10. $11 is equal to log IP over I naught. And then swapping it around into exponent form. To I naught. And I also multiply both sides by I naught there, just to expedite this a little bit. All right, so now we're going to do the same sort of thing as we did with the earthquakes, is now we have the intensity of the power saw in sound, the intensity of the conversation in sound. And so this ends up being a ratio of these. How many times more intense is the sound of the power saw? So the one that we're saying that is more intense or a measurement is the one that goes in the numerator. And if we divide by I naught, if we divide I naught 10 to the 11 by I naught 10 to the 6, then of course this factor of I naught divides out, and we end up with this ratio of sound intensity is equal to 10 to the 11 minus 6 equals 10 to the 5 equals 100,000. Therefore, saw intensity is 100,000 times as much. So the sound's intensity is 100,000 times as much. But notice what we essentially did here is we compared the sound intensity of two things, and it ended up being equal to, now this ends up being a little clunkier, that if we're subtracting those two decibel levels, we also had to divide it by 10. So decibel 1 minus decibel 2 over 10. That division by 10 was converting it to bells instead of having this in decibels. And that happened. Where did that happen in our step? That happened when we divided both sides by 10 in those two places. But essentially, this is what we are going to be using. Again, you will always be given any formulas for this, so you don't have to memorize them, but understanding kind of how they work is probably a really good idea to do. All right, next page. The next one we're going to look at is we're going to look at pH scale. And so your familiarity with this might depend on if you took chemistry or if you just saw this in science. But regardless, we kind of need to account for this. How this works, just to remind you if it's been a while since you've seen pH is measuring how acidic a solution is, or how alkaline a solution is, or the other word is basic for alkaline. And we have this scale, whereas 0 is the most acidic and 14 is the most alkaline. And so right in the middle is a neutral solution. And so we say that pure water is neutral. And so that's a score of 7. And we can think of them as a score because it's just kind of this arbitrary measurement. Well, I suppose it's not arbitrary. What it is measuring is hydrogen ion concentration in this solution, measuring it in moles per liter. And again, we don't really need to get bogged down with the details of what this meant in chemistry class or whatnot. You do need to recognize that a 0 is more acidic and a 14 is more alkaline. And so if you're being asked for which one is more acidic or which one is more alkaline, then that's going to affect what you're dividing when you have your ratio set up. So we need to be careful about that. So here's our formula. It tells us that pH is equal to negative log of H plus, and H plus is just your variable for hydrogen ion concentration, moles per liter. All right, so in question 3, it says how many times more acidic is vinegar, which has a pH of 2.8, than baking soda, and baking soda is an 8.2. So here's your vinegar is 2.8 on this scale. Here's baking soda, which is an 8.2. And we're trying to figure out how many times more acidic the vinegar is. So the vinegar stuff we will put in our numerator when we're comparing these intensities. All right, so to start with this formula, we have the fact that pH is equal to negative logarithm of H plus. And if we do this for vinegar and have those as little subscripts, so we have negative 2.8 if I substitute my pH for vinegar and I multiply both sides by negative 1 is equal to logarithm of H plus of vinegar. Swapping this around into exponent form so we can solve this for H plus, we get H plus of vinegar is equal to 10 to the negative 2.8. Baking soda, pH of baking soda is equal to negative log H plus of baking soda. Plug in our 8.2, multiply both sides by negative 1. We have negative 8.2 is equal to log of H plus, swapping it around into exponent form. H plus is equal to 10 to the negative 8.2. Now I want to reiterate that we need to be clear about which way we're taking this ratio. This question is asking how many times more acidic is vinegar. Vinegar is more acidic, it's towards the acid end of this scale. If it asked the other way around, how many times more alkaline is baking soda, then we would put baking soda in the numerator. We're asking for how many times more acidic the vinegar is, so we'll put that in our numerator. Also be careful about the exponents because these exponents are negative numbers and because we're dealing with very, very, very small numbers. But as long as you follow around what happens with our exponent laws, you'll be okay. And so now we go to compare how many times more acidic this is, then we end up with H plus of vinegar over H plus of baking soda is equal to 10 to the negative 2.8 divided by 10 to the negative 8.2. We subtract our exponents. So we are subtracting negative 8.2. And we end up with 10 to the 5.4. Should convert that into our numerical answer and conclude that therefore vinegar is 251,189 as acidic and baking soda. So notice this again. This looked, by the end, this really looked pretty similar to what we were doing with earthquake and what we were doing with sound as well. It's just comparing the intensity of sound, comparing the intensity of the earthquakes is equal to 10 to the exponent of the difference of their measurements. And so, again, doing very similar thing with pH. Last question. Number 4 says an earthquake in Relay is 126 times more intense than an earthquake in Morocco. If the Morocco was a 6.2, then what was the magnitude of Relay? Okay, so if Morocco, our Morocco earthquake ends up being a 6.2 is equal to log of IM over I naught. Swapping this around, IM over I naught is equal to 10 to the 6.2. Is equal to I naught 10 to the 6.2. Relay, we do the same thing. But we have MR is equal to logarithm of IR over I naught. Therefore, IR I naught is equal to 10 to the MR. Therefore, IR is equal to I naught 10 MR. So MR is what we're trying to solve for. It's the magnitude of our Rayleigh earthquake. And just like before, if I divide these out, now let's be careful. The Rayleigh is 126 times as intense as the earthquake in Morocco. Say Rayleigh is the larger earthquake. So we want the larger earthquake. We'll put that in the numerator. Rayleigh earthquake, IR was equal to I naught times 10 to its measurement. Morocco, I naught times 10 to the 6. Divide out factors of I naught. Now the right side just ends up being 10 to the Rayleigh's magnitude minus 6.2, which is the Morocco magnitude. But the left side of the equation, this is told to us. This is told that we have a Rayleigh earthquake is 126 times as intense. So that ratio of intensities is equal to 126. We swap this around into logarithm form. And this ends up being 126 is equal to MR minus 6.2. We add 6.2 to both sides. And we get logarithm of 126. We add 6.2 to that. MR ends up being 8.3. Therefore, Rayleigh earthquake has a magnitude. And that's all. All right, as always, if you have any questions, please let me know. Thanks so much.